Hi, here's the second part of a two-object kinematics problem with a time shift, a time delay. The problem: a smart car and a Maserati are planning a 300-meter race. Because the smart car has less acceleration, it gets a 1/2 second head start. The acceleration for the smart car is 3.0 meters per second squared. The acceleration for the Maserati is 3.5 meters per second squared. Assuming, unrealistically, that the cars can keep up this acceleration for the duration of the race, when does the Maserati catch up with the smart car? And based on that, who wins the race? All right. Now, the previous video, I solved it using a method where I said, well, if the Maserati is in motion for a certain amount of time t, then the smart car has a 1/2 second head start. They are in motion for t plus 1/2 second. What I'm going to do now is solve it without having to worry about putting a t or a t plus 1/2 into the charts. But I do end up needing to have two smart car charts. Okay, x initial, x final, v initial, v final, a and t. So what we're going to do to solve it this way is I'm going to say, well, in that first 1/2 second, in that 1/2 second head start, how far has the smart car moved? How fast is it going at the end? And then I can start my timer, really, my t equals 0, at 0, and the smart car and the Maserati will both have the same time. So let's think through this. In a 1/2 second head start, how far has the smart car gone? So I have a 1/2 second here. I know my acceleration, plus 3.0. I'm starting from rest, and I'm starting at the 0 because that's where I chose it. So I want to know, where are we at the end of that 1/2 second, and how fast are we going? Because once I know that, then I can say, now the smart car's up here, and my Maserati's there. They're both going to have the same amount of time to their meeting point, which means this t and this t are going to be the same, because I took into account the 1/2 second right there. This is a pretty straightforward kinematics problem. I know initial position, initial velocity, acceleration, and time. I need to solve for x final, and I need to solve for v final. So hit pause and solve for those two yourself. Okay, so if you got these answers, you probably did it right. So in 1/2 second, the smart car, let's not do it that way. The smart car ended up moving a whopping 0.375 meters. Yeah, okay. And it is traveling at the highly unsafe speed of 1.5 meters per second. Oh my gosh. All right. Now I know where this is. I know how fast it's going. And I can put all that information into my charts here. Okie dokie. Now, my initial position isn't the origin. It's going to be 0.375 meters. X final is my question mark. That's what I want to know, where they have the same final position. V initial, no longer at rest. We've started moving already. We are moving at 1.5 meters per second plus. And I have 3.0 still for my acceleration. All right. And then my time is just time. Maserati, still back here, starts at 0. It's still at rest. And its acceleration is 3.5. in the positive direction. All right, so we have the final position of these two is the same. That's what we want to know, is where do they meet up? Where is the Maserati catching up with the smart car? And based on that information, who wins the race? Okay, let's do it. Just like last time, just like that. I am going to set x final of the smart car to be x final of the Maserati. That's the definition of how we've set this up. We're saying these are the same place. And then I'm going to replace this x final with the equation for x final. So it's going to be x initial smart car plus v initial smart car time for the smart car. Well, conveniently, time is the same. I don't need a subscript. Plus 1/2 acceleration smart t squared. So this is x final smart car. I'm going to set that equal to x final Maserati, same idea, x initial m plus v initial mt plus 1/2 acceleration mt squared. Very similar to the equation we had in the previous way we solved this problem. Let's do our zeros. Again, I like at this step to say, what can I get rid of? Where are my zeros? Okay, smart car. And now I'm ignoring this because I'm only wanting the match time. Smart car has nothing that's 0. Bummer. Well, thankfully, the Maserati is still at the origin, and it is still at rest. Okay, so from 6 terms, we're down to at least 4. Now I'm gonna, at this point often I will dump some numbers in. So let's see what we've got. X initial smart car, 0.375, plus V initial smart, 1.5 T, plus 1/2 A 3.0 T squared equals, gone, 1/2 acceleration of the Maserati, 3.5 T squared. All right, I have an equation that the only unknown is time. And it's clearly a quadratic because I have a t squared, a t, and a non-t term. So let's rearrange to get it into the format for solving the quadratic equation. I'm going to move everything over to this side because most things are on this side already. So if I have 1/2 of 3.0, that's 1.5. Half of 3.5 is 1.75. Okay, so subtract this over. 1.5 t squared minus 1.75 t squared gets you, negative 0.25 t squared. And then this stays the same, plus 1.5 t. This stays the same, plus 0.375 equals 0. And now this is in the right format to solve the quadratic equation. Go ahead and do that. And see if your numbers match mine. So hit pause, solve this one. Okay, those are my 2 numbers. And conveniently, they're the same as the numbers from the other way we solved it. That's a nice little way to make us feel good about how we're solving it. Again, which one do we use? We're dealing with time. We are just saying time is 0. We don't have negative time. We only move time forward. We're going to use this. And we're going to do the same thing. We're going to solve for x final smart and x final Maserati. This one's the easy one. So it's 1.75 times time squared. 6.24 squared. And if we do that, pretty sure we come out with 68.14 again. And then here, x final for the smart car, that's going to be, I need space for this, 0.375 plus 1.5 times the time, 6.24, plus 1/2 of 3.0, times time squared, 6.24 squared. X final for the smart car is 68.14. All right. They match up, which means probably did it right. And is it a reasonable number? I guess so. Maserati's, even though it looks like not much more acceleration, apparently it counts for a lot with that 1/2 second of head start. Okay, so that's a second way to deal with this type of problem when you have a time change, a time head start or a time delay. And pick the one you like better. Which one makes more sense to you? This is kind of a 2-step method, but the algebra is a little bit easier when you get to this part. Or you could do, as in the previous video, the 1-step method, but that has slightly more complex math. They both get you the same answer, and they're both perfectly valid ways of solving these problems. Go with whichever one makes more sense to you. All right, thanks for watching.